Welcome, scholars. Get ready because in this explainer, we're diving into the universe's ultimate accounting system. We are going to fundamentally change the way you look at everyday effort, movement, and the invisible forces that make absolutely everything around us happen. But hey, before we get to the formulas and the physics, I've got to ask you a serious question. Have you ever pushed yourself to your absolute physical limit? I mean, exhausted all your energy, sweat literally pouring down your face, only to achieve exactly zero results?
Well, according to the strict laws of physics, yes, you totally have. Here's the ultimate gotcha punchline. If you step up to a massive concrete brick wall right now and push on it with all your might for, say, 3 straight hours, you might be completely exhausted, but physics says you did zero work. None. Nada. Why? Well, let's find out.
Okay, let's dive into this. Here's our roadmap. 1. The universe's ultimate currency. 2. Drawing the system boundary. 3. Work, where force meets displacement. 4. Power, or the rate of effort. 5. Math in motion. And finally, 6. A summary of the system.
All right, part 1. The universe's ultimate currency.
So everything starts with energy. By definition, energy is a measurable physical quantity that describes the capacity to do work or produce heat. You can kind of think of it as the ultimate fuel tank of the universe, or maybe like an athlete's physical stamina right before they run a massive marathon. Because without energy, the entire universe is completely frozen. Nothing moves, nothing heats up, nothing changes at all. It is literally the fundamental fuel tank for all physical reality.
Moving on to part 2. Drawing the system boundary.
So if energy is the currency of the universe, how do scientists actually keep track of all this cosmic cash without losing their minds? Well, physicists draw an imaginary line called a system boundary. Think of it like balancing a budget, right? You can't track your money if you don't know which bank accounts belong to you. Basically, everything inside this boundary is the system, and everything outside is the environment. And this brilliantly illustrates how drawing boundaries allows us to track kinetic wind energy entering a turbine system, transforming into mechanical rotational energy, transferring to the generator system, and finally outputting as electrical energy to light up a bulb. These boundaries literally make the invisible visible.
Which brings us to part 3. Work, force meets displacement.
Now that we know how to track energy, it's time to talk about how we actually move it. In everyday conversation, work usually means, going to a job, clocking in, or sitting at a desk doing your homework. But in physics, work has a highly specific meaning. In physics, work is the primary mechanism for transferring energy into or out of a system. And here's the kicker. It only counts if you actually force an object to move.
Now, what's really interesting about this is that for work to happen, you absolutely need 2 distinct things, force and displacement. The formula is beautifully simple, honestly. Work equals force multiplied by distance. And by the way, both work and energy are measured in a unit called joules. So when a person pushes a crate across the floor, they're applying an act of force and moving it. Energy is transferring from their body to the crate. But remember that brick wall from earlier? You applied force, sure, but the distance the wall moved was 0. And any force multiplied by 0 distance equals 0 work. That is the golden rule of physics. No displacement equals no work.
All right, part 4. Power, the rate of effort.
That brings us beautifully into our next concept. So we know how to measure the total amount of energy transferred, but what about how incredibly fast we can transfer it? Well, this is where power enters the chat. If work is the total amount of energy you transfer, power is how fast you transfer it. Let's use a physical analogy. Imagine your work is draining a massive swimming pool. You have to move all that water. That is a set amount of total effort. But power? Power is the difference between draining that pool with a tiny little garden hose versus bringing in an industrial fire hose to blast it all out at once. The fire hose has way more power because it does the exact same amount of work in a fraction of the time. It's exactly why walking up a flight of stairs feels totally fine, but sprinting up that exact same flight leaves you gasping for air. You did the exact same work against gravity, but your body had to generate a massively higher power output to do it faster.
Moving on to part 5, math in motion.
All right, scholars, take a deep breath. It is time to tackle the math. But I promise you, it's breezy, it's entirely manageable, and we are going to do it together. Let's look at our first scenario. A student pushes a heavy robotics cart down the school hallway with a constant force of 45 newtons. They push the cart a total distance of 12 meters. So how much work did the student actually do on the cart?
Okay, we're going to use the universal 4-step physics math process to conquer this super easily. Step 1, identify your variables. Our force is 45 newtons and our distance is 12 meters. Step 2, choose your equation. Well, we know work equals force times distance. Step 3, plug those numbers in. That's 45 times 12. And finally, step 4, calculate the final answer, 540 joules. That student actively transferred 540 joules of energy to that cart. See? Easy.
Now, let's move on and see how this builds when we flip the equation around. Here we have a motorized winch doing 3,000 joules of work to pull a heavy rock prop across a theater stage. The winch pulls with 150 newtons of force. So, how far did the prop move? Well, we use the exact same formula, but we just solve for distance. So, distance equals work divided by force. We plug in 3,000 joules divided by 150 newtons, and boom, the prop moved exactly 20 meters. Now let's briefly tackle power calculations. Power is simply work divided by time, and it's measured in watts. Let's look at an elevator motor. If it does 12,000 joules of work in just 4 seconds to lift the car, we divide 12,000 by 4 to get a power output of 3,000 watts. Now compare that to a standard 800-watt microwave. If we needed to do 24,000 joules of work to heat up some leftover pizza, we can just flip the equation to solve for time. 24,000 joules divided by 800 watts means it's going to take exactly 30 seconds for hot, cheesy perfection.
And finally, part 6. Summary of the system.
Look at that. You've officially conquered the concepts and the math. Now it's time to bring absolutely everything we've learned together into a neat, organized package for your notes. So the crucial point is understanding the distinct differences between these two concepts. Work is the transfer of energy, measured in joules, calculated by force times distance. Power, on the other hand, is the rate of that transfer, measured in watts, calculated by work divided by time. Consider this comparison your ultimate cheat sheet for any upcoming tests, so definitely make sure you understand the difference between a joule and a watt.
Let's do a quick rapid-fire review. Energy is the universe's capacity to do work. We use system boundaries to track exactly where that energy is flowing. Work is how we transfer that energy, but remember, it absolutely requires displacement. And one last reminder, sweating and pushing against a stationary brick wall still equals zero work. Finally, power is simply the rate of that effort, basically how fast you get the work done.
Thank you so much for watching. If you found this video helpful, informative, or entertaining, please give it a like and subscribe. Every subscriber helps me so much and means the world to me. Also, feel free to comment any questions you might have or requests for future topics. And remember, scholars, keep your mind open, your spirit curious, and your heart kind.